operating system, mostly based on the pre-M30 patch and then the Xenomai extension for the kernel. First, I will do some reminders about real-time. What is a real-time system? It must respect what we call the deadlines. And the deadline is the time between the start of the work, executing the code, and the completion of the work. And this time should be inferior of the period of the task. The first example of real-time systems started in the 60s for the Apollo program. It was an operating system based on OS 3.6.0 and called RTOS 3.6.0. But it was not embedded, it was used for controlling the mission. There are two ways for managing tasks in an operating system. The first way, the very famous way, is the time sharing with the GPOS such as Linux or Windows or whatever, Unix or any kind of operating system for general purpose OS. There is no time constraint, and all the tasks have the same priority and the same way to run, actually. And what we talk is a real-time operating system with a time constraint, which means there is a concurrency between the task and we should manage the deadline that we said before. So real-time means to manage priority. There are several ways to manage priority of a task. Static way with some famous scheduling algorithms such as RMS or such as POSIX, but it could be dynamics with some algorithms such as EDF, which is available now in the Linux kernel. And the second characteristic is a task switching, which is called a preemption when a higher priority event occurs. Here is an example of managing tasks with the RMS algorithm. It is a very simple algorithm which based on the simple concept as the shortest task, period task has the highest priority. It's very famous, very simple to implement. It's the default algorithm of the RTOS operating system, which is used in the space industry or in military, which was used for military industry and now in the space industry. And we have an example of 3 tasks. And the first task, which is T1 with a short period, has a higher priority on the T2 and, of course, on the T3. So here we can see an example of preemption of the T3 task by the T1, and then an example of preemption of the T2 by the T2 or on the T3, and then of the T1 on the T3. Okay, so it's quite simple. We can talk in the Linux environment. We can talk about the difference between hard and soft real-time. In industrial system, we talk always about hard real-time, which means the deadlines should be met. There is no possible to have what we call an overriding. Software real-time is a way to get better performances without strict deadlines. It's what we use in a Linux system, for example, for some system based on the network, video conferencing, games, etc. But that's not the subject of my conference. We will I will explain how to make Linux be a hard real-time system. Some real-time operating systems which are very famous. Lots of real-time operating systems are proprietary, such as LynuxWorks, which is the most famous and still used in space industry or military industry. It was designed by Wind River. Pisos, it's the same. It's an old operating system, but it was designed by Wind River too, or it was bought by Wind River. The RTX, Lynx OS, Micro COS 2, they are all proprietary systems with real-time capabilities. There are some open source systems such as RTOS, as I said before, FreeRTOS, ECOS, Zephyr. And in the industry, as it's quite simple to design a real-time algorithm, there are lots of homemade operating systems in big companies. Unix-like operating systems, such as Linux, are not real-time operating systems. They are designed to share to have the same priority for all the tasks, actually all the users. And you need to patch the kernel. The only way to get RT behavior on Linux is to patch a kernel with a preempt-RT, which is the official patch from the Linux Foundation, with RTAI, which is an operating system which was done at École Polytechnic School of Milan in Italy, and of course Xenomai, which is the most famous, one of the most famous extensions for using Linux as a real-time system. Of course, all the embedded OS are also RTOS. So Linux is based on the Unix principles. So it was based on processes, initially based on processes. The first thread implementation was available in 2.6 kernel, which is quite a long time ago. But well, it was not at the beginning of the Linux kernel. It was an emulation of the processes. Threads were emulated by processes, and there are two execution modes for a process. The first one is the user space, and the second one is the kernel space when you call a driver or when you call some system calls inside the kernel. So it's quite complex to manage because we have a complex memory management with the hardware addresses. If you check with the lspci command, you can check the hardware addresses of the board. And there are kernel addresses inside the driver, for example, which is based on managed by the MMU. And inside the processes, you have a virtual address for each process in user space. So it's quite difficult to manage the memory. In some lots of RTOS, such as RTMs, you don't have a MMU, and you don't use the MMU of the processor. Sometimes you use it, but most of the time you don't use the MMU, and so you have access from an application or for a kind of driver. You have access to the hardware memory, and so you can access to the hardware controllers directly. But there is no memory protection between the user and the kernel. A good way to test a real-time system on Linux is to start a periodic task, as we saw before for RMS, and you can compare the major deadline with a theoretical deadline, and the difference is called the jitter. Of course, you need to do the test with a heavy load, because if you don't have a load on the Linux system or any kind of operating system, you will get good results. There are some tools, of course, open source, and the tools are provided with the most famous projects, such as preempt-RT or Xenomai. Cyclic test is one of the programs I use. It's provided by the preempt-RT project. Latency is quite similar to cyclic test, but is provided by the Xenomai project. You can use the GPIO and put a scope on the GPIO to get the behavior of the signal. I will show you some video later. And for the system load, to generate a heavy system load, you can use Hackbench. You can use Duel from the Xenomai project. You can try to do throttling by sending lots of packets on the Ethernet interface. And finally, you can trace the results by using the good old GNU plot, which is very, very powerful and very nice to use. There are some scheduling issues on Linux. This is why you need to patch the kernel. There is no full preemption event in the kernel mode. So in Linux kernel, when you get an interrupt, the first part of the interrupt is called the top half, and the second part is the bottom half. And the first part of the interrupt handler, which is the top half, is not possible to interrupt the top half. So it could be an issue, and it could generate some jitter. Regarding the preemption, you can have a fixed period with the constant, which is called aged, and with the configuration inside the kernel, which is called config aged and a number. As we can see in the literature on website on the kernel documentation, the one thousandth value is a low latency configuration, which is so okay. On the recent kernel, you can use most of the time you use a tickless mode, which means you can wake up the kernel when the system is idle and when you need to wake it up. But of course, waking up is not deterministic, so it's not a way to get real-time behavior. It's just a way to save energy on a laptop, for example. There is a feature in the Linux kernel which is fine for if you don't use as a real-time operating system with hard real-time, which is called the real-time scheduler throttling. You can configure the real-time task bandwidth is limited to 95% of the bandwidth, of the full bandwidth, which means even if you have a task eating all the CPU, you can still have a running kernel with a correct response time. It's fine for the user, but it's not fine for the real time because it's not a real time behavior. Is an example of recording with a scope on a Beagle Bone Black, which is a Cortex A8 and 1 millisecond period, and of course something such as Hackbench to generate AV load. So you can see the signal is very bad, has a very bad appearance, and there is it's quite a problem, even if the period, which is 1 millisecond, is not that difficult to manage. So if you want to improve the RT kernel performances, there were for the old versions of kernel 2.4, there were some preemption patches and the preemption patches were integrated in the 2.6. They are still available in the current kernel, even for the version 5. But it's mainline, but it's absolutely obsolete and it's not useful at all. Now the most famous patch for the Linux kernel is the Preamp 30, which is managed by the Linux Foundation and which is partially integrated in the last version, in a recent version, which is 5.15. Second way is to use a kernel approach, which was defined by RT Linux a long time ago, then RTAI and currently Xenomai. Of course, you need to use a real-time policy. In POSIX, it's SCAD FIFO or SCAD error. You need to lock the memory to avoid the page fault with the mlocal system call. You need to disable some way to save the power. If you configure a kernel with Xenomai, you will get some warning message as a configuration if some features such as APM are not disabled. You can use the CPU affinity to set some threads on some CPU, on some cores. And of course, you shouldn't use the signal handling. With the POSIX timer, you will generate a signal handling at the end of the period, and it's not real time at all. So you need find a way to manage a periodic task with another operating system call. Sorry. So some word about Preamp 30. It's kind of some history. The work started a long time ago with MontaVista, TimeSys, and LynuxWorks, and they post some real-time patch at the beginning of the century. And Ingo Molnar, who is a major kernel maintainer, re-implements the parts of the patch and post a first version of the real-time preemption patch. And it was a core team, the beginning of the core team about the Preamp 30, which is quite different, absolutely nothing to do with the previous patch for the 2.4 kernel. So Preamp 30 is an experimental branch for the 2.6 kernel, started for the 2.6.9. It was maintained by Thomas Gleisner, who is the chairman of LynuxWorks. And it's an official Linux. It has been the official Linux Foundation project since 2015. It can work on platform defining the Arch support RT flag. It's published as a patch for the mainline kernel, or in some BSP, for example, for the Raspberry Pi, you have a branch with a patch applied, which is very simple, because if you use a kernel from a BSP, most of the time it's difficult to apply the patch because the patch is designed for the standard and mainline kernel. So it's a good way to have a branch for the pre-RT, because it's much easier to integrate on the system. It's the same programming API as a standard kernel in user space or kernel space, the same drivers. And as I said before, it was merged in the 5.15, but we still need a smaller patch. It's not absolutely merged with the kernel. So here is an example of configuration for a kernel. It's a branch for the Raspberry Pi I got from github.com, the Raspberry Pi kernel. And so you have to select, you can see the default configuration at the beginning of the configuration screen. But if you want to have a nice RT behavior, you need to validate the last option, which is fully preemptible kernel. If you want to test the preempt-RT performances, you need to build a system, an image with the preempt-RT, and it's quite easy to do with the build root or Yocto, because it's just a patch. You use the RT-test package, which includes cyclic test and Hackbench, for example. And you can create 5 threads, for example, with 1 millisecond period. Start the thread with a priority 99, and the first one will get a priority 99, the second one 90, and etc. And the -n means you need to use the nanosleep system call to sleep between the periods instead of using a senior. So nanosleep is a clock nanosleep is a way to get real-time behavior in a system, Linux system. And on another screen, you need to start the Hackbench. The Hackbench with -G20 means you will start 20 groups of 40 processes, which mean 800 processes talking with each other and sending 1,000 messages. So it generates lots of system calls, so it generates a heavy load on the system. If you do some measurement, you can notice the maximum jitter with the standard kernel is about maximum 3 milliseconds. It could be 1 or 2 or 3, depending on the system and depending on the behavior of the distribution. But with the preempt-RT, it's not. It's around 100 microseconds. So is a recording of cyclic test. Inside cyclic test, you have a way to generate an histogram. So you can plot the histogram with GNU-plot, and you can see the maximum value is less than 90 microseconds. The same measurement with the standard kernel, you can see the maximum value is close to 2.5 milliseconds. So it's a very different graph. Okay. Now we will talk about the co-kernel, which is a very different technology, which was defined by RT Linux at the beginnings. The approach is very different, as you use a standard Linux kernel with a small patch, but the Linux kernel doesn't run in real time. You have a co-kernel running the real-time task, and the RT kernel is dedicated to the real-time task. It's only possible on the RT kernel for the RT kernel to run real-time task and no standard task. The real-time subsystem is based on kernel modules, and there is a virtualization of the interrupts and lots of system events based on a kind of microkernel. There are several models. The first one in the beginning of the century was a kernel-only system called RT Linux, designed to run the task in kernel space. The second one was a fork of RT Linux and called RTAI in Italy, and with a partial user space integration. And the current Xenomai version has a full user space integration, and you can run a task in kernel space or user space, but most of the time you use user space because of licensing, of course. Because if you run your task in kernel space, you should put your code in. You could use the GPL for your code. So some words about the co-kernel principles. There is a RT-specific scheduler, a microkernel which handles the hardware events such as interrupts. So the interrupts are not managed. The interrupt controller is not managed by the kernel, Linux kernel anymore. It's managed by the microkernel. So you get the hardware request here, IRQ, for example, and the microkernel will send when we send the pseudo IRQ to the real-time task or to the kernel, depending on the driver, which register the IRQ. So in this kind of system, the Linux kernel is an idle task of the RT kernel, which means any Linux task has a lower priority than any RT task. RT Linux was the first project based on such an architecture. It was designed by two students, Victor Yodeiken and Michael Barabanov, in the New Mexico Institute of Technology. It was licensed under the GPL v2 because it runs in kernel space. There were lots of contributions because it was very, very nice to use with very good result compared with the pre-and patch I mentioned before. And there was a commercial version by a company founded by Yodeiken and Barabanov, which is called FSMLabs. And they defined a patented technology, which was not very nice for the open source community. And there was a conflict with the Free Software Foundation regarding the licensing, and there was an agreement. If you use an agreement called the open patented license. So if you use the open source version of pre and RT Linux, it was possible not to be to respect the patented license, the patent. So RT Linux was quite famous in the USA or for US Army, for example, or US Navy. And so Wind River core both the RT Linux technology some years ago in order to avoid the concurrency of RT Linux on LynuxWorks. But it was a way to kill the product, and the last GPL version, which was obsolete, already was retired by Wind River for the website. And as far as I know, RT Linux is not used anymore. So here is a simple graph about the RT Linux architecture. And so you have the hardware controller, so interrupt controller. You have a RT Linux kernel which means you need to patch the kernel, and you have the two parts of the running kernel in the kernel space. The first part, of course, is the Linux kernel with no real time, and with the Linux modules with no real time. And the second part is the RT Linux part with a RT scheduler, POSIX API in the kernel, which was very nice because in user space you have a POSIX in user space, but you don't have POSIX in the kernel space. So it was a very nice feature from RT Linux. And the third box is your application. So as the application runs in kernel space, you need, if you want to communicate with a Linux process, for example, to send the data somewhere on, or to put the data on a graphical GBI, you need to use the real-time FIFO or shared memory, and it was quite difficult to use, it leads to licensing issues because of the real-time application in kernel space. So it's recording of RT Linux GPL a long time ago. I did it myself, by myself, on x86 system. As you can see, it's a long time ago, but with a loaded system or not loaded system, so it's in French, you have quite the same response, and the maximum of jitter is lesser than 20 microseconds. So it's fine. It's very fine, very nice. So RTAI was a project. It's still a project designed by Paolo Mantegazza from the Politecnico Milano. It's a fork of the RT Linux. It was designed for teaching and research because they didn't want to buy LynuxWorks by Wind River or any proprietary operating system. So they designed a fork of RT Linux for their own use. It was focused on x86. They started a project to be able to execute user space task as a real-time task, and there was a collaboration with Xenomai, with Philippe Jérôme, who is the founder, the author of the Xenomai, and they start to collaborate to create RTAI fusion. And but there was some personal problems between Philippe and Paolo, so Philippe left the project and started a new project called Xenomai 2. The current version is still active, and it's 5.3. So Xenomai was designed by Philippe Jérôme, who is a very famous French engineer in the real-time technology. It was designed for RTOS emulation on Linux. For example, you can get your LynuxWorks code and compile it on Linux and run it on Linux. But at the first time, it was not based on real-time capabilities. So there was a collaboration with RTI to be able to run Xenomai with real-time capabilities, and also to design a new way to virtualize the IRQ and the events not to be under not to use the RT Linux patent. So it's based on a microkernel, which was called ADOS. It's a bit different now. The first version was called ADOS, and a concept of an interrupt pipeline, which is called ipipe. On the new version, which is Xenomai 3, you have two choices. The first one is a co-kernel with a Cobalt kernel, which is the most used because it's a standard way of using a dual kernel system. But there is a single kernel approach, which is called Mercury. And so it's possible to run Xenomai skins over the preempt kernel. But as far as I know, it's not very used, and I don't know if it will be still available in the next versions. The current stable version is 3.2.1, and there is a new approach designed by Philippe to instead of the interrupt pipeline, because the interrupt pipeline is a bit difficult to port and to maintain. So the new approach is called Dovetail. So currently in the last version of stable version of Xenomai, you can use Dovetail for recent kernels, and you can use ipipe. You must use ipipe for the older kernel. So for the next version of Xenomai 4, it will only be based on Dovetail. So while using Dovetail, ipipe is very difficult to adapt and maintain. We can talk about it at Smile CS because we did it several times for customers. And so it's very difficult because it's designed for a standard kernel, mainline kernel, and most of the time the BSP for the board are not mainline, so you have to adapt the patch. It depends on the platform. For IMX, for example, it's a bit difficult for the recent IMX. It was okay for IMX 6. It's not okay for IMX 8. You need the specific patch. And so The dovetail is very different, and so you it will improve the integration of the co-kernel because you can use it with a Linux kernel directly enabled with the Linux kernel. There is a simplified maintenance as long as it's out of the tree, and maybe there is chance to upstream the Xenomai 4. So with the dovetail, inside of patching the kernel with the iPipe, we use the dovetail ready kernel based on the main line. So you should adapt the kernel, but it's much easier to adapt than the previous patched kernel. So is a schematic of the architecture, a picture of the architecture of the Xenomai 3 with the Cobalt approach. So you have the application. Here, your application with using the glibc. You select, sorry, it's in French. You select the emulator, which means the skin, for example, the POSIX. Most of the time we write the code in POSIX. The replacement of the glibc for the RT part is a libcobalt. In the kernel, you have the Cobalt layer, and then the iPipe. And the iPipe is hardware dependent, and you need to adapt it on the system on chip because, for example, of the interrupt controller used by the system on chip. The Mercury approach is much simpler because it's based on the Linux plus PRNTRP, only with the glibc and using the skins. For example, POSIX or LynuxWorks. But if you use POSIX, it's not very interesting to use Mercury. It's interesting if you want to use another skin such as LynuxWorks or Ficheux or whatever. So Xenomai is very efficient. If you compare the results with Pream30, it's much better, 2 or twice better than Pream30. So now the task RT task run in user space. There is no licensing program because the libraries use the LGPL. There are skins for the real-time operating system API, POSIX, LynuxWorks, RTX, etc. And it's used and maintained by big companies such as Siemens. So the first maintainer of Xenomai is the guy from Jan Kiska, which works as Siemens. There are some drawbacks as Xenomai is a small community. It's not inside the Linux Foundation. There are lacks of documentation and examples. The internal documentation is not that good, and I think there will be some documentation with the EVL project and Dovetail, but it was difficult to adapt because of the lacks of documentation. Cobalt is a bit more difficult to install, to set up, because you need to install the user, then the kernel apart, and there are specific drivers with the API called RTDM. So some debug tools are not available or are available, but a bit more difficult to use, such as Ftrace for the real time. It's possible to use Ftrace with Xenomai, but it's quite limited. The events you can trace are quite limited. And of course, there were no support from the Linux Foundation. So how to install Xenomai with iPipe-based on an iPipe-based version? You need the kernel sources, the Xenomai sources, the iPipe sources, which is a patch, and you create the Xenomai compatible kernel with a script called prepare kernel. So you call prepare kernel.sh with minus Linux with the kernel path. You define the architecture, which could be ARM, ARM64, or etc. And you give the path to the iPipe patch. You configure the user space library with AutoTools, with configure minus host equal cross tool chain. It works on SMP. It's based on SMP, and there is no Xenomai ready distribution. And there are some Xenomai ready distribution, Pream30 ready distribution from Red Hat, for example, but it's not available for Xenomai.
But there is a Buildo support in mainline and the Yocto support with Mita Xenomai. I took an old project and I redesigned the Mita Xenomai layer to integrate Xenomai in the Yocto build system. So here is the kernel configuration. When you patch the kernel, for example, with it's a standard kernel, you need to use a standard kernel. Here it's for Raspberry Pi, but it's for the standard kernel. You will add the patch will add an entry which is called Xenomai Cobalt, and you need to activate, but it's activated by default. You need to activate the extension in the kernel configuration. You can test the performances, and the procedure is very close to the Preamp31 with the periodic task and system trace. Xenomai provide latency and cyclic test. You can start latency with a default period of 1 millisecond and use, for example, Duel, which is a replacement of Hackbench, but you can still use Hackbench if you want. Duel, which is a replacement of Hackbench designed for Xenomai. And the maximum jitter for the P3 is less than 40 microseconds. If you run it on x86, it's about 5 or 10 microseconds, so it's very nice. So is an example of a GNU-plot graph with based on latency results. So you can see the results are less than 35 microseconds, and with most of the jitter in under around 5 microseconds. Some words about the domains and the iPipe. The guest OS, such as Linux or Xenomai, for the microkernels, they run in prioritized domains. And of course, Xenomai runs in the highest priority domain. The Linux kernel runs in the lowest priority domain, and for all the events, interrupts or exception or whatever, the domains may handle events or give it up back to the pipeline and put it give it to Linux. If the IRQ is for Xenomai, the Xenomai will take it and handle it. If the IRQ is for Linux, the IRQ will be sent to the Linux domain, but in the second time. Is a small graphic to show the iPipe. You have an IRQ coming from the iPipe. It's not for the highest priority domain, so it's passed to the root domain and handled by the Linux kernel. So of course you can't lose the hierarchy inside the Linux domain. Some words about the Linux RT development. You can, of course, it's very important to develop applications in Linux RT. Preamp RT is very straightforward because it's a Linux kernel with the same API for the kernel and for the user space. So you use the POSIX API from the glibc, which is designed in libspace thread. You use the kernel API for the driver. You can use the Ftrace for real-time profiling or tracing the events, such as the SCAD wake-up. We will show some example later. So it's very simple. So talking about the Ftrace profiler, it was designed by Steven Rosdet from Red Hat. No, he's not at Red Hat anymore. He's working for Google. It was mainline. It's a tool for kernel profiling. Most of the time you use it to profile the kernel function, new driver functions, something like that. But you can also trace events. It's based on the TraceFS in syskernel debug tracing. As it's not that easy to use, you can use a trace-cmd command to record and report events, or you can use a Qt-based tool, which is called kernelshark. As an example, if you want to trace a kernel function, you can insert a driver, and you say to trace-cmd to record the function of the driver. You do the job with accessing
driver, and then if you stop the trace-cmd, you will get the result with trace-cmd report, and you can see the calling process of the function, the CPU number, the timestamp, and the name of the system call, which was called by misc open, for example. So it's very nice to measure the performances of your drivers. If you want to use it for real time, it's a bit different because you don't record the function, but you record events. And for example, if you use trace-cmd record on SCADE wake up with the command program line, you will record the behavior and timestamps of the program if it is a periodic task. And then with the trace-cmd report and the filter command, you can get the result you can give to GNU-plot. So with the color, you can see the different fields of the report. The first one is the name of the PID, the name and the PID when the event occurred. So it was Hackbench on CPU 0 at timestamp here. The event was SCADE wake up, and so my example task wake up at this time, and so it started and interrupted Hackbench because it's a real-time task, and Hackbench is not a real-time task. So there are some specific fields. If you find idle 0, it's not a real process. It's a kernel swapper, what we call it's a scheduler. And if you have 3 dots and the number the PID, it's a process name which is not mapped into the PID. It means the process. The documentation is not that clear, but I think it means the process was started after the trace-cmd started. The record was started. So we can see some examples. We can use a periodic task on a P3 with a period of 500 microseconds. Of course, a pre-entity kernel, a SCADE FIFO, and priority is 99. We trace the SCADE wake-up event, and we use a clock nanosync syscall to manage the task, the periodic task. So it's the best configuration. And if you trace the record, you can see that most of the points all the points are around 500 microseconds. If we change the configuration, oh, it's okay, nothing more. So Xenomai is a bit different because Xenomai is a Linux program running using Xenomai libraries and Linux libraries. It runs on 2 domains. One domain which is called the NRT, which is Linux based, and the RT domain, which is based on Xenomai. It's a main. There is a main managed by Linux, and when you create the threads in real time, the threads are managed by Xenomai, only by Xenomai. So there is some ways of migrating from. You can see a small picture. Here is the main. Here is the NRT thread using NRT driver in the Linux kernel. The blue part is a RT thread using the RT driver in the Xenomai kernel. You can communicate between the 2 parts with XDDP, and if you call a system call from the RT of the Linux kernel from the RT, it's called a migration, and so it could lead to RT problem. So the Xenomai schemes, there are some Xenomai schemes, which is the first one is Alchemy, which is a native scheme, but it's not it's used, but as is a specific scheme API. It's much better to use the POSIX, to have PSOS, LynuxWorks, Smoky to test RTDM for the kernel space, and of course the several schemes. You can load several schemes at the same time. So if you want to design an application, you should segregate the RT and the NRT code with the RT for Xenomai and NRT for Linux. You select an API. There is a way for the test to force the calling of the, for example, pthread create from the LEE3 thread by using the real prefix. It's only for the test. The cross toolchain for Xenomai is produced by the build system. There is a specific variable which is called sdir, which should be used, and there is a script generated by Xenomai, the Xenomai build system. And in case of build root or Yocto, you need to have this xenoconfig script to get the name of the compiler, the C flags, or the LD flags, etc. And it is very nice to use it with the script. And so most of the time the makefile is based on xenoconfig. And for example, you can get the CC name with xenoconfig --cc. Regarding the skin, you can get the C flags for POSIX, the C flags are native, etc. There are some external projects for CMake support, but right now it's not integrated in the CMake, in the Xenomai project. Sorry. So there is a specific entry which is called /POC/Xenomai to get the statistics of the real-time tasks. For example, you have here a Xenomai pthread, two Xenomai pthread running in the Xenomai domain. But actually, there is only one real-time Xenomai pthread with a priority of 99, and the first one is the main, it's called a shadow task because actually it's managed by Linux, but you can see it from Xenomai domain. So you can see the context switch, and you can see the migration, and there was only one migration when you start the thread, so it's okay. XDDP is a way to communicate the data between RT and NRT domains. It's based on the RT side. It's based on the socket designed specifically for Xenomai. It's a UDP port from there are 32 UDP port, and on the NRT side, Linux, it's a shard driver with dev RTP0 to dev RTP31. It's not possible to use the POSIX IPC as it's not the same domain, but if you want to make two tasks communicate using the POS on the same domain, it's possible to use the POSIX IPC. So there are some examples in the Xenomai source, and one of them is XDDP echo, which is a communication between, so it's a communication between NRT and RT. So in RT, you send the task, which is read by the NRT, and so the NRT can write to the XDDP device node, and you get it from the port. So RTDM is a real-time driver model. So it's a Xenomai API for the kernel space. It's an abstraction just like on Linux for the drivers, and there are only two kinds of driver for XDDP for RTDM. Sorry. The main device, which is similar to a shard driver for hardware, CAN, serial, etc., or any kind of board, and the protocol device stack for the network driver, such as RTNet or XDDP, was designed by the protocol device stack, and there is a RTNet, which is an implementation of a network stack in real time. So it's a Linux module, but the driver is a bit different. It's quite similar, except you can use the syscalls in most of the time in the RT domain, but you can still use the syscalls in NRT if you want to call them from Linux thread. So it's an example of it's not very interesting for you. The RTDM driver is a Linux module. As I said before, the RTDM syscalls can run in both domains. Xenomai and Linux is very close to the Linux kernel API, but it's not exactly the same. You have different prototypes of the functions, etc. And it's very close to the Linux approach regarding the ERQND. I can show you something. I don't think if it's possible to change the presentation. Maybe it's a bit dangerous, so I will end the presentation. And if you have some question, I can show you some demonstration. I don't. It's the first time I use this tool, so and it's web-based, so it's not my culture. The last slide is about UDD. UDD is a way to develop drivers, mostly in user space, user device driver. It's similar to UIO for Linux. It's very nice because most of your code will be in user space, and so it's much more easy to debug, and there is no GPL issue. You need, of course, you need a short kernel driver to allocate the resources. Most of the time memory or IRQ, and the user space program manage resources, and you can access the memory with the mmap system calls, which is very, very famous in the Linux environment. And in user space, you can get the IRQ directly from the user space because it's mapped by UDD to a signal, specific signal, which is called signal from cgrt-min to cgrt-max. And cgrt-min and to cgrt-max are signal dedicated to real time. So if you have questions, I will be happy to answer. Any question? If you don't have question, I can show you an example of Xenomai. There are 10 minutes left. So question maybe in the chat. No problem. We have better latency, but what is the cost to use RT Linux instead of non-RT Linux? Actually, there is no what I don't know what you mean with cost. If it's a bit more difficult to develop, but regarding the CPU, I don't think there is any additional cost, and it's the same for footprint because Xenomai and Preempt-RT are very small patches, so. There is quite no difference with the standard Linux system. So I can show you an example. For example, I can share my screen, my whole screen instead of sharing only a window. So I will share my screen. I hope you can see my screen. And for example, I can show you an example of. So in my videos, there is an example of Xenomai in real-time mode. So it's a periodic task, and there is a hackbench behind, but you can see the system is very stable. It's done with a scope, small scope. So it runs in the RT domain. If I do the same with Linux. In the Linux domain with a Linux timer, POSIX Linux timer, we can see the difference, of course, and the signal is not stable at all. So it's a bit difficult to have such a signal in a real-time application. Okay. So as an example, I can show you a terminal. So it's an example of using Xenomai. I will reboot the board. So it's an implementation of Xenomai on a build root system for Raspberry Pi. So I run the system. So I have some example, for example, of I can insert RP driver, or I can insert, for example, kernel task, insert mode kernel task. Okay. So I have a kernel task running inside of the Xenomai. I can remove the kernel task and insert a driver for using the GPIO. It's called RTDM. No. GPIO RTDM.ko, and now I can start an example, Xenomai RTM minus P 500 micro. And so I can see the jitter for the RT and the jitter for the NRT. This is the example I record with the oscilloscope. Okay. So you can see even with any kind of load, the latency, but it's not very. I didn't record the maximum value, but you can notice the latency for the RT is much better than the latency for the NRT. Okay. No question. No question. Yes, I know we are, but I don't lose to put the presentation in full screen, because most of the time when I present, I modify the slide. I modify the slide at the same time. So, okay, nothing to add.